Hi, I'm Dalya Cohen, and today I will be talking about acids and bases. I will first discuss how acids and bases are formed and what they exactly are. Then I will discuss strong acids and bases versus weak acids and bases. I will talk about pH, what it is and what it represents. I will talk about acids and bases in everyday life, where you can find them, what they do, and what they're used for in industries throughout the world, and specifically in Canada. So what exactly is an acid and a base? Well, there are a couple theories about what they are. The first was developed in 1887 by a man named Sven Arrhenius. Now, this theory stated that an acid is a substance that dissociates in water to produce one or more hydrogen ion. A base, it says, is a substance that dissociates in water to form one or more hydroxide ions. Some problems with the Arrhenius theory of acids and bases can be exemplified with this simple equation. Hydrochloric acid, Arrhenius said, would dissociate in water to form hydrogen ions and chloride ions. When scientists examined this theory, they assumed that Arrhenius had taken into account the interaction that hydrogen chloride would have with water. However, when we look to this equation, we can see that Arrhenius hadn't completely taken water into account. When hydrogen chloride reacts with water, it creates hydronium ion and chloride. Now, in this equation, we see that the hydronium ion does not exist, and thus this reaction is not correct. So, a second issue with the Arrhenius theory of acids and bases is that some bases, such as ammonium and calcium carbonate, do not have hydroxide ions in their original form. However, when dissociated, they react with water in such a way as to form these hydroxide ions. The Bronsted-Lowry theory of acids and bases overcomes the issues that arose with the Arrhenius theory of acids and bases. In 1923, two chemists working independently of each other proposed similar theories. Those two were Johann Bronsted, working in Denmark, and Thomas Lowry, working in London. Together, their ideas formed the Bronsted-Lowry theory of acids and bases. This theory states that an acid is a substance from which a proton can be removed, and a base is a substance that can remove a proton from an acid.
The standard scale of measurements for acidity and basicity is known as the pH scale. Here is a range of acids from extremely acidic at 0 to neutral at 7. And here is a range of bases starting at neutral at 7 until extremely basic at 14. This scale was developed in 1909 by a Danish physicist named Søren Sørensen. From his findings, pH can be defined as the negative log of the concentration of hydronium ions.
Now that we understand acids and bases a little bit more, let's look at two types of acids and bases. The first are strong acids and strong bases, and the second are weak acids and weak bases.
A strong acid or base is an acid or base that dissociates completely into ions when diluted in water. A weak acid or base is an acid or base that dissociates slightly when diluted in a water solution.
Here we have an example of a strong acid. Hydrogen chloride combines with water to create hydronium ions and chloride ions. Hydronium ions have the same concentration that the hydrochloric acid did to begin with. Here we have an example of a weak base. Because the ammonia does not contain the hydroxide ions, it is not an Arrhenius base. However, it is a Bronsted-Lowry base because it is able to remove the proton from the water.
Some examples of strong acids are hydrochloric acid, hydrobromic acid, and hydroiodic acid. Some examples of strong bases are sodium hydroxide, potassium hydroxide, and calcium hydroxide.
One type of reaction that occurs between acids and bases that is extremely important both in understanding acids and bases and in the way they are used in our lives is a neutralization reaction. Here we have the addition of an acid and a base to form water and a salt. Our example is hydrogen chloride mixing with magnesium hydroxide. Now the acid and the base are opposites, and thus when combined, they balance each other out and neutralize each other. So the hydrogen and the hydroxide combine in a double displacement reaction to form water. And in the same way that these two combine, the chloride and the magnesium combine over here to make magnesium chloride. Now we are going to talk about acids and bases and their uses in different industries in the world, as well as their uses in households and in everyday lives. Over here we have an example of one type of base that is used in many people's lives daily. It is the antacid. Now there are four main types of bases that antacids are formed from. The first is an aluminum salt, such as aluminum hydroxide. The second is a magnesium salt, such as magnesium carbonate or magnesium hydroxide. The third is calcium carbonate, and the fourth is sodium bicarbonate. Here I have an example with me of an antacid, and this is an antacid that is 500 milligrams of calcium carbonate. Hi, so now we are going to do a little bit of an experiment. We are going to test the pH of water, Tums dissolved in water, which is our lovely antacid over here, Tums dissolved in lemon juice, and regular lemon juice. So the first step will be to be testing the pH of water. We next take our lemon juice, take a little bit on the spoon, take out our handy dandy pH paper. Next, we will take out our Tums. So that won't touch the air. So first, I will drop the Tums in water and we will mix it up to see what happens. Next, we will take our second Tums and we will put it nicely into the lemon juice and we will start dissolving it. This is the piece of pH paper that was tested with water that did not have the antacid dissolved in it. This is a piece of paper that has the pH paper that had the water that had the antacid dissolved in it. This is a piece of pH paper from the lemon juice without the antacid dissolved in it. And lastly, this is a piece of pH paper with the antacid dissolved in the lemon juice.
Although stomach acid is more acidic than lemon juice, these results give us an idea of the neutralization reaction that would occur between the stomach acid and the antacid.
Acids and bases play extremely important roles in many industries worldwide today. Things such as the production of fertilizers contain sulfuric acid, phosphoric acid, and nitric acid. Explosives rely on nitric acid, ammonia, which is nitrogen dihydride. Soaps contain sodium hydroxide. Many foods contain baking soda, which is sodium hydrogen carbonate, phosphoric acid, vitamin C, and folic acid.
A new study underway examines the high levels of folic acid and its relation to cancer development. A recent study by Dr. Kim of the University of Toronto found that high levels of folic acid in baby lab mice can lead to a higher probability of developing tumors as they grow up. Although this topic isn't fully understood yet, this study is a very early one that will hopefully be the first one of many to come.
Although there are many benefits of acids and bases in everyday lives and as well in industries throughout the world, there are a few risks that can be very prevalent. For example, some acids and bases can be very strong in concentration. When an individual comes in contact with acids and bases that are very strong, they can cause corrosive burns and injuries that can potentially be fatal. Some acids and bases that are found in foods, when consumed in large quantities, can become very dangerous for an individual, as mentioned before with the folic acid study that has recently been done. Despite the risks of acids and bases, they are essential to our day-to-day lives. From food to car batteries, from toothpaste to detergent, acids and bases are essential to our day-to-day lives, and we would not be able to survive without them.